Since the dawn of time, human beings have lifted their eyes to the night sky and wondered, what is all of this? What are those shining lights? Where do we fit into this grand, mysterious picture? For most of history, the answers were wrapped in myth and imagination. We thought the stars were candles hung in a dome, or that Earth was the center of everything. Yet, over centuries of curiosity, questioning, and science, we have begun to peel back the layers of mystery. Today, we can explain the difference between the universe, galaxies, solar systems, and the vastness we call space. And yet these words, though familiar, describe concepts so staggeringly immense that our minds struggle to hold them. To truly feel the difference, we need to embark on a mental journey, zooming out from the ground beneath our feet to the very edges of everything that exists. Imagine starting right here on Earth. It feels big to us, stretching with oceans and continents, mountains and deserts, life everywhere. But Earth is not alone. It belongs to a family, a gravitationally bound system we call the solar system. At its heart blazes the sun, a star so massive that it contains more than 99% of all the mass in the system. The sun is a nuclear furnace, converting hydrogen into helium, releasing light and heat that bathe our world and make life possible. Around this blazing star, 8 planets trace their elliptical paths: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Each has its own character, its own moons, its own story. Alongside them drift countless smaller bodies, asteroids, comets, dwarf planets like Pluto, and endless grains of dust. All of these together, bound by the sun's gravity, make up our solar system. It is our immediate cosmic neighborhood, the place we call home. But even as vast as it feels, stretching billions of kilometers from the sun to Neptune, the solar system is tiny in the next step of scale. Because our solar system is just one among hundreds of billions inside a much larger structure, a galaxy. To understand this, picture the solar system as a single house. A galaxy, then, would be an entire city made up of billions of houses. Galaxies are enormous, gravitationally bound collections of stars, gas, dust, dark matter, and mysterious forces. And our particular galaxy is the Milky Way. The Milky Way is a majestic spiral stretching about 100,000 light-years across, with sweeping arms of stars curling outward from a central bulge. In that central region, hidden from view, astronomers believe lies a supermassive black hole called Sagittarius A Asterix, whose mass is millions of times greater than our Sun. Around it, the galaxy spins slowly, and our solar system takes about 225 million years to complete one galactic orbit around the galactic center. Just imagine, every time Earth makes one galactic orbit, hundreds of millions of years have passed, continents have shifted, species have risen and fallen. That's the scale of our city of stars. The Milky Way contains perhaps 200 to 400 billion stars, and each of those stars could host its own solar system. That means hundreds of billions of potential homes, worlds, and perhaps even life. And the Milky Way is not even unusually large. It is just one galaxy among trillions. Across the observable universe, astronomers estimate there may be as many as 2 trillion galaxies, each containing billions or trillions of stars. Some galaxies are small and irregular, with just a few million stars. Others, called giant ellipticals, can stretch hundreds of thousands of light-years across and hold more than 1 trillion stars. Galaxies cluster together, pulled by gravity, into groups and superclusters, which themselves link into vast filaments and walls of matter stretching across billions of light-years. Seen on the grandest scales, the universe resembles a cosmic web, with galaxies forming strands of glowing nodes, and in between them, vast voids of almost empty space. Now let's pull back even further. If a galaxy is a city, then the universe is the entire country, the entire planet, all the cities, all the oceans, all the land, everything. The universe is the sum of all that exists.
all galaxies, all stars, all solar systems, all matter, all energy, and even the space-time fabric itself are part of the universe. The word universe means everything, everything we can observe, and even perhaps the things we cannot yet detect. It includes not only the luminous stars and galaxies we see through telescopes, but also the invisible ingredients, dark matter, which exerts gravity yet cannot be seen, and dark energy, the mysterious force that drives the expansion of the universe faster and faster. The universe is about 13.8 billion years old, beginning in an event we call the Big Bang. Not an explosion in space, but the expansion of space itself. Since then, galaxies have been flying apart, carried by the stretching fabric of space, and the cosmos has grown into the vastness we see today.
But then comes the question, what about space? If the universe is everything, what role does space play? Space is the stage on which this cosmic drama unfolds. It is the seemingly empty expanse that stretches between stars and galaxies. Yet space is not truly nothing. It has structure. It can bend and curve, as Albert Einstein showed in his theory of general relativity. Massive objects like stars and planets warp the fabric of space. And this curvature is what we feel as gravity. Space is filled with particles, fields, radiation, and quantum fluctuations. Even in the deepest voids between galaxies, there is still a faint background glow, the afterglow of the Big Bang, the cosmic microwave background radiation, whispering to us across 13.8 billion years. So space is not an empty container, but a dynamic, flexible fabric that makes the existence of the universe possible. Now, let's piece it all together in a way that truly captures the scale. Imagine yourself standing on Earth, looking up at the sky. The moon circles our planet. Together, Earth and the moon orbit the sun. The sun, along with its family of planets, forms our solar system. That solar system is just one of hundreds of billions orbiting inside the Milky Way galaxy. The Milky Way is just one of trillions of galaxies, spread across a universe that may be infinite. And all of this is held within the fabric of space. Each term, solar system, galaxy, universe, and space, describes a different layer of scale, a different rung on the ladder of existence. To give a sense of proportion, think of this analogy. If the solar system were the size of a coin, then the Milky Way galaxy would be the size of North America, and the universe, it would stretch far beyond our imagination, with countless other coins scattered in all directions, each one representing another solar system in another galaxy. The mind reels at these scales, because human brains evolved to think in meters and kilometers, not in light years and trillions of stars. But this is the true scope of reality. What's fascinating is how our understanding of these concepts has evolved. Ancient civilizations thought Earth was the center of everything. The stars were fixed points in a heavenly dome. It wasn't until Copernicus, Galileo, and others that we began to understand Earth was a planet orbiting the sun. Then in the 20th century, Edwin Hubble showed that the Milky Way was not the entire universe, that other galaxies existed far beyond. And today, with telescopes like Hubble and the James Webb, we see thousands of galaxies in a single patch of sky, each one containing billions of stars. Our perspective has expanded step by step, each discovery pushing the boundaries of what we thought everything meant. Yet despite all this knowledge, the differences between these terms remain crucial. A solar system is a single star and its planets. A galaxy is a vast city of stars, each with its own solar systems. The universe is all the galaxies and all the space that contains them. And space itself is the stage, the fabric of distance and time, the silent stage on which the play of creation unfolds. And perhaps the most humbling truth is that all of it, every galaxy, every star, every planet, may still be just a tiny fraction of something greater.
Some scientists speculate about the multiverse, the idea that our universe may be one bubble among countless others. If that is true, then even the universe may not be the final answer, just as the solar system was not. But whether or not there are other universes, one thing is certain. We, small creatures on a small planet orbiting an ordinary star in an ordinary galaxy, have found a way to know. We have asked questions, built telescopes, launched spacecraft, and used our minds to imagine beyond our sight. So the next time you hear the words universe, galaxy, solar system, or space, remember that each describes a level of scale, a step outward into the infinite. The solar system is our immediate home. The galaxy is our city. The universe is our everything. And space is the fabric that holds it all. Together, they form the architecture of reality, the structure of existence itself. And we, for a fleeting moment in cosmic time, get to be aware of it, to marvel at it, and to wonder what else might lie beyond.
When you look up at the night sky, the stars seem so close, as if you could almost reach out and pluck them from the darkness. But appearances deceive. Those pinpoints of light are not just far away, they are unimaginably distant. The human mind evolved to measure in steps, in meters, in kilometers at most. We understand the distance across a city, the span of an ocean, maybe even the circumference of the Earth. But the cosmos? The cosmos laughs at such scales. For that, we need a new unit of measurement, a way to talk about distances so large that normal numbers break down. That unit is the light year. But what exactly is a light year? How does it help us understand the universe, and how do scientists use it to map the infinite? To answer these questions, we need to begin with light itself. Light is the fastest thing we know. It moves at about 300,000 kilometers every second. In the blink of an eye, light could circle Earth more than 7 times. It is the speed limit of the universe, the ultimate ceiling that nothing with mass can break. Because of this, light becomes our ruler, our cosmic measuring tape. If you ask how far away something is, astronomers often answer in terms of how long light takes to reach us from that object. A light second is the distance light travels in 1 second, about 300,000 kilometers. A light minute is the distance it travels in a minute, about 18 million kilometers. A light year is the distance light travels in 1 year. That is about 9.46 trillion kilometers, or nearly 6 trillion miles. A single light year is so vast that it's hard to imagine. If you drove a car at highway speeds without stopping, it would take more than 10 million years to cover just 1 light year. Now think of this. The moon is about 1 light second away. The sun is 8 light minutes away. The nearest star beyond the sun, Proxima Centauri, is over 4 light years away. That means the light you see from it tonight left the star more than 4 years ago. You are not seeing it as it is now, you are seeing it as it was then. And this is the strange magic of the light year. Because light takes time to travel, every time we look into space, we are looking into the past. The farther away something is, the older the light we see from it. Look at the Andromeda Galaxy, the nearest large galaxy to ours, and the photons hitting your eyes began their journey more than 2 million years ago, before modern humans even existed. Look deeper still with a telescope, and you can see galaxies whose light has traveled for billions of years. To look outward is to look backward in time. But how do we actually measure these distances? How do astronomers know that a star is 10 light years away rather than 20? The answer is not simple. It requires layers of methods, a cosmic distance ladder built step by step. For nearby stars, the most reliable method is parallax. If you hold your finger out and close one eye, then switch eyes, your finger seems to jump against the background. That shift is parallax, caused by viewing from 2 different angles. Astronomers use Earth's orbit around the sun as a baseline. By measuring the apparent shift of a star against the distant background over 6 months, they can calculate its distance using geometry. This method works well for stars up to a few thousand light years away. Beyond that, parallax becomes too small to measure. So astronomers use standard candles, objects whose true brightness is known. If you know how bright something truly is, and you know how bright it looks from Earth, you can calculate how far away it must be. Certain kinds of stars, like Cepheid variables, pulse with a regular rhythm, and their period of pulsation reveals their intrinsic brightness. By comparing that with their apparent brightness, we can measure their distance in millions of light years. Type Ia supernovae, exploding stars that always release a similar amount of energy, are another kind of standard candle, letting us measure even greater distances. And for the most distant reaches of the cosmos, astronomers rely on redshift, the stretching of light waves as the universe expands. The farther away a galaxy is, the faster it moves away, and the more its light shifts toward the red end of the spectrum. By measuring this redshift, scientists can estimate distances in billions of light years. So, the light year is not just a number. It is the language of the cosmos. It allows us to talk about places so far away that ordinary words collapse. But it is also a reminder of time. Because every light year is also a year into the past. The farther we look, the younger the universe we see. The James Webb Space Telescope, for example, can see light that has traveled for over 13 billion years, showing us galaxies that formed just a few 100 million years after the Big Bang. In that sense, astronomers are not only explorers of space, but also time travelers, peering back into the earliest chapters of creation. The scale becomes dizzying when we try to grasp it. Our Milky Way galaxy is about 100,000 light years across. The nearest large galaxy, Andromeda, is 2.5 million light years away. The Virgo cluster of galaxies is 50 million light years distant. And for the observable universe itself, stretches about 93 billion light years in diameter. Think about that, 93 billion light years. And yet that is only the part we can see. Beyond that horizon, light has not had time to reach us in the 13.8 billion years since the universe began. The actual universe may be much larger, possibly infinite. But even with all this, humans have found ways to make sense of it. We give the distances names, we build analogies. Imagine shrinking everything down. If the Earth were the size of a grain of sand, the sun would be a ball about the size of a grapefruit sitting a few meters away. The nearest star would then be hundreds of kilometers away, and the Milky Way galaxy would stretch across entire continents. That is the kind of scale we are dealing with. The light year also shapes how we think about the possibility of contact with other civilizations. If a planet were 100 light years away and we sent a message today, it would not arrive until the year 2125. If they replied immediately, we would not receive the answer until 2225. Communication across interstellar distances is not like making a phone call. It is like throwing a bottle into an ocean of time and waiting centuries for a reply. Which is why, even if intelligent life exists out there, the vast distances measured in light years make encounters incredibly difficult. And yet this unit, so immense, so beyond ordinary comprehension, is part of everyday work for astronomers. When they describe a star as 20 light years away, they are casually describing a distance of nearly 200 trillion kilometers. But it is not just about numbers, it's about perspective. To speak in light years is to embrace the vastness of reality, to admit that we live in a universe far larger than our minds evolved to handle. And in a way, that humility is beautiful. So the next time you look at the stars, remember this. The light entering your eyes is ancient. It may have left its source before your ancestors were born, before humans walked upright, before Earth had continents in their current shapes. Every starlit night is a time machine, a journey backward through history. And every measure we make in light years is a reminder of both our smallness and our ability to grasp the infinite. The light year is more than a unit of distance. It is a bridge between human minds and the cosmos, a way to speak about the unspeakable, a ruler for infinity. Look up at the night sky. Above you stretches a canvas of darkness, dotted with stars that twinkle faintly from unimaginable distances. It feels peaceful, mysterious, and endless. But here's the question that has puzzled thinkers for centuries. If the universe is filled with billions upon billions of stars, why is the night sky dark? Shouldn't the heavens blaze with light, as bright as the surface of the sun, if stars are scattered everywhere in every direction? It seems obvious at first that the sky should shine, but it doesn't. The night is mostly black, a vast emptiness with only scattered points of light. This question, known as Olbers' paradox, has fascinated scientists and philosophers for hundreds of years. To understand the answer, we need to take a journey through history, through the nature of light, and through the very structure of the universe itself. The puzzle begins with a simple idea. If the universe is infinite, static, and filled with stars, then in every direction you look, your line of sight should eventually land on a star. Imagine standing in a forest. If the forest goes on forever, no matter where you look, your vision will eventually hit a tree trunk. In the same way, if the universe stretches forever with stars scattered evenly, then every line of sight should end on a star's surface. The sky should glow uniformly bright, not dark. And yet, when we look up, that is not what we see. Early thinkers struggled with this paradox. In the 16th and 17th centuries, when the telescope was still a new invention, scientists like Johannes Kepler pondered the darkness of the night sky. Kepler wondered if perhaps the stars were finite, that maybe the universe simply did not contain enough of them to fill the sky with light. Later, Heinrich Olbers, the German astronomer after whom the paradox is named, considered whether the darkness could be explained by dust clouds blocking the starlight. Perhaps, he suggested, space was filled with interstellar dust that absorbed the light of distant stars. But this solution did not hold up. If dust absorbed light, it would heat up over time and eventually glow itself, producing radiation until the sky was again bright. Clearly, something deeper was at play. The true answers to Olbers' paradox emerged only in the 20th century as our understanding of cosmology expanded, and the explanations reveal profound truths about the universe. The first key lies in the fact that the universe is not infinite in age. The cosmos had a beginning. About 13.8 billion years ago, the universe began with the Big Bang. That means the light from the most distant stars has not had enough time to reach us yet. We live inside a kind of cosmic horizon. Beyond a certain distance, light simply hasn't had time to arrive, so those regions remain dark to our eyes. The night sky is black not because stars aren't there, but because their light has not yet reached us across the immense gulf of time and space.
The second key lies in the expansion of the universe. Space itself is stretching, and as it expands, the light traveling through it is stretched as well. This stretching increases the wavelength of the light, shifting it toward the red end of the spectrum, a phenomenon called redshift. For the most distant galaxies, the redshift is so extreme that their light has moved out of the visible range altogether, becoming infrared or even microwave radiation. We cannot see it with our eyes, so those regions of the sky appear dark. In reality, the universe is glowing, but much of that glow is invisible to us. The cosmic microwave background, the faint afterglow of the Big Bang, fills all of space. But it shines in microwaves, not visible light, so the night sky remains black to human vision. A third factor is the finite number of stars. While the universe contains an astonishing number of stars, perhaps sextillions, their light is not evenly spread across the sky. Stars are grouped into galaxies, galaxies into clusters, and clusters into filaments, separated by vast voids of empty space. These gaps mean that even within our observable universe, there are lines of sight that do not end in starlight, but in emptiness. And though our eyes adjust and perceive individual stars as bright points, the spaces between them remain dark. Put all these pieces together and Olbers' paradox dissolves. The night sky is dark because the universe is not infinite in age, because its expansion stretches light beyond visibility, and because stars are clumped unevenly across the cosmos. Far from being a flaw, this darkness is a clue, a window into the true nature of the universe. If the sky were bright everywhere, it would mean we lived in an eternal, unchanging cosmos. But the darkness tells us the universe had a beginning, that it evolves, that it is structured and dynamic. Still, the paradox lingers in our imagination because it plays with intuition. We think of infinity as overwhelming, as something that should fill everything with brilliance. Yet infinity, combined with time and expansion, leaves us with darkness. And within that darkness, the stars we do see become all the more beautiful. Each one is not just a point of light, but a survivor, a messenger whose photons manage to cross the gulf to reach us. When you gaze at the night sky, you are seeing not the absence of light, but the traces of cosmic history, the ancient glow of nearby stars, the faint signals from galaxies millions of years away, and the silent testimony of a universe still expanding into mystery. But the question also raises a deeper wonder. If the night sky is dark because the universe's structure, then what would it look like in another kind of cosmos? Imagine a universe that was infinite and eternal, with no beginning. Imagine stars evenly spread across infinite space. In such a place, the sky would blaze without end, as bright as a star's surface. There would be no night, only eternal day. Life might not even be possible because the constant bombardment of radiation would scorch every world. In that sense, the darkness of our sky is not just a curiosity, it is a gift. It makes planets habitable. It allows night and day. It gives us the chance to sleep under stars instead of being burned by their unending light. There is also a philosophical beauty in this truth. The darkness of the night sky is not emptiness, but evidence. Every patch of blackness is a record of distance and time. Every gap between stars is a clue that the universe has edges, at least in what we can see. And in that darkness lies the possibility of the unknown, galaxies too far, civilizations too distant, mysteries too deep for their light to reach us yet. The blackness is not absence, but potential. So the next time you step outside on a clear night, look carefully. Notice the velvet blackness surrounding the stars. Realize that what you are seeing is the signature of the Big Bang, the expansion of the cosmos, the limits of time itself. The darkness is not nothing. It is the reason we exist. The stars we see shine all the brighter because they are framed by infinite night. And in their faint light, we are reminded that we are part of a universe that had a beginning, that is still expanding, and that holds mysteries yet unseen. The question, why is space dark if stars are everywhere, may sound simple, but its answer contains the keys to cosmology, to the nature of light, and to the fate of the universe. The night sky is dark because the cosmos has a history, because time has a beginning, because space is still stretching. And in that darkness, the story of the universe is written, waiting for us to look up, to wonder, and to understand.
In the grand theater of the cosmos, few objects inspire more awe, fear, and fascination than black holes. They are invisible giants, cosmic traps from which nothing can escape. Not matter, not radiation, not even light itself. They warp space, stretch time, and challenge our deepest understanding of physics. For centuries, they were only theoretical, whispers in the mathematics of gravity. But today, we know they are real. We have seen their effects on stars, captured their shadows with telescopes, and even heard their collisions through the ripples of space-time. But what exactly is a black hole? How do they form? What kinds are there? And what mysteries do they still hold? To answer these questions, let us step closer to the most extreme objects in the universe. A black hole begins its life, paradoxically, with death. When a massive star reaches the end of its fuel, it can no longer support itself against a crushing force of gravity. For millions of years, the star burns hydrogen into helium, then helium into heavier elements, layer upon layer like an onion. But eventually it reaches iron, an element that cannot produce energy through fusion. At that moment, the balance breaks. Gravity overwhelms the star's pressure, and the core collapses inward in a catastrophic implosion. The outer layers are blasted away in a supernova explosion, brighter than billions of suns, while the core shrinks into something so dense, so compact,
that space itself caves around it. If the remnant is heavy enough, more than about 3 times the mass of our own sun, it collapses past the point of no return, creating a black hole. At the heart of every black hole lies what is called a singularity, a point of infinite density where the known laws of physics break down. Surrounding it is the event horizon, the ultimate boundary. Cross it, and there is no way back. The escape velocity there, the speed required to get away, exceeds the speed of light. Since nothing can outrun light, nothing can escape. To an outside observer, objects falling toward a black hole appear to slow down, stretched by gravity, fading away as if time itself is stopping. In truth, the object crosses the horizon quickly, but from the outside, it is lost forever, hidden beyond the veil. Not all black holes are the same. Astronomers classify them by size. The smallest are stellar mass black holes, born from collapsing stars with masses of a few to dozens of suns. Then there are intermediate black holes, harder to detect, weighing hundreds or thousands of suns. Their origins are still mysterious, perhaps formed by mergers of smaller black holes or runaway collisions of stars. At the largest scale are supermassive black holes, giants with millions or billions of solar masses, lurking in the centers of galaxies. Our own Milky Way harbors one called Sagittarius A*, about 4 million times the mass of the Sun. Some galaxies contain black holes so huge they power quasars, cosmic beacons that shine brighter than entire galaxies as matter spirals into the abyss. And beyond even these, there may exist primordial black holes, tiny relics from the earliest moments of the universe, perhaps no larger than an atom, but with the mass of a mountain. If they exist, they could explain some of the dark matter that fills the cosmos. But black holes are not just about size. They are about mysteries. What happens inside? Does the singularity truly exist, or will a new theory, perhaps quantum gravity, replace it with something else? Does information fall into oblivion, or is it somehow preserved on the horizon, as Stephen Hawking proposed? This is known as the black hole information paradox, one of the deepest puzzles in physics. According to quantum mechanics, information can never be destroyed. According to general relativity, black holes swallow it forever. Reconciling these two truths is one of the great challenges of modern science. We have begun to probe black holes not only with light, but with soundless vibrations of spacetime itself. In 2015, the Laser Interferometer Gravitational Wave Observatory detected ripples in spacetime caused by the merger of 2 black holes more than 1 billion light-years away. For the first time, we could hear the universe through gravity's music. Each merger produces a final burst as the black holes coalesce into one, releasing more energy in a fraction of a second than all the stars in the observable universe combined. And in 2019, the Event Horizon Telescope unveiled the first image of a black hole shadow, a glowing ring of hot gas around the abyss at the heart of galaxy M87. Humanity had seen the unseeable. Black holes also play a paradoxical role in the growth of galaxies. Far from being only destroyers, they act as engines. As matter swirls into them, it heats to incredible temperatures, blasting out jets of energy that can shape entire galaxies. In a way, black holes help sculpt the cosmos, regulating star formation, stirring interstellar gas, and influencing the structure of galaxies on vast scales. Without them, the universe might look very different. And yet, the mysteries deepen. What happens if you fall into a black hole? According to relativity, you would experience spaghettification, stretched like a strand of pasta as gravity pulls harder on your feet than your head. But beyond the horizon, what occurs is unknown. Some theories suggest a wormhole, a tunnel to another universe. Others propose a firewall of energy at the horizon that would destroy anything entering. Still others imagine that black holes may not end in singularities at all, but in new universes budding from their depths. Perhaps every black hole is the seed of a new cosmos, and our universe itself was born from one. Black holes challenge the limits of imagination. They force us to confront infinity, to ask questions about time, space, and reality itself. They are the ultimate laboratories, where gravity is so intense that quantum theory and relativity collide.
To solve their mysteries is to move closer to a theory of everything, a single framework that unites the large and the small, the cosmos and the quantum. And perhaps that is why they hold us spellbound. They are not just astrophysical objects, but symbols of the unknown. They represent both danger and possibility, both endings and beginnings. They remind us that the universe is not tame, not small, not simple. It is vast, strange, and full of wonders we have yet to grasp. So the next time you hear the phrase black hole, remember that it is more than just a void. It is the corpse of a star, the engine of a galaxy, the puzzle of physics, and perhaps the doorway to realities we cannot yet imagine. In their darkness lies the light of understanding, waiting for us to look deeper, to listen harder, to think beyond. Black holes are not the end. They are the beginning of some of the greatest mysteries science has ever known.